Assalamu alaikum guys, how you doing? Today we're going to talk about slabs, and particularly we're going to mention one-way slabs. Two-way slabs, you probably will cover that in RC 2. I have divided up this presentation into two. One will talk about solid slab and a small brief introduction, and the other part will mainly talk about the ribbed slab. So to start off, we know that the floors, beams, and girders are all usually poured together, which means that it's going to form what we call a monolithic system. So if you look at the floor plan over here, this one right there, we can see that the slab or floor is distributed over B2. Here the beams are B1, B2, B3. We also have beams B4, B5, and B6, and we have girders G1, G2, and G3. So the slab mainly is carried on the beams B1, B2, B3. Then those beams are distributing the loads to the girders, mainly G1, G2, G3, and then the girders are distributing the loads to the columns. The exception is beams B4, B5, and B6 because they are distributing the load directly to the column. And here's a section AA, this one, which shows that we have about 10 beams. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So this is how the loads are distributed. So they go from the slab to the beams, from the beams to the girders if they're present. If not, they will go from the beams directly to the columns, and then from the columns they will move on to the foundations. We have two types of slabs, as I mentioned earlier. We have one-way slabs and two-way slabs. One-way slabs, we also have two types. One is a solid slab and the other is a ribbed, or what we call ribbed joist floors. And for a slab to be qualified as a one-way slab, this ratio must be satisfied, which is the long span divided by the short span should be equal to or more than 2. So if you look at this floor plan right here, what made this into a two-way slab is the presence of this beam right there. So basically means you control if you want to make a slab into a one-way slab or a two-way slab. So if you remove this beam, and if that beam is not there anymore, then this will become a two-way slab, which means the loads will be carried on this beam, this one, and that one as well. And we kind of briefly mentioned how the loads get transferred in courses like Structure 1 and Structure 2. Okay, but again, here mainly I'm just concerned with one-way slabs. So with the current situation that we're having right here, then the loads probably are going to be divvied up this way, this way, and that way. Okay, so this middle beam right here is carrying more, it's carrying, again, usually this is divided up into two, and like this, so this beam will carry this whole area, while this beam will carry this, so this is carrying half of that panel, let's say, or slab, and this one is carrying the other half. So this is how one-way slabs are going to act. Okay, moving on to two-way slabs. Again, here I'm just mentioning what they are. We can have two-way solid slab, two-way ribbed slab, flat plates, flat slabs, waffle slabs, and I'm sure you're going to cover all those in RC 2. Usually the spans in two-way slabs are larger than the one that are used for one-way slabs. Usually for one-way slab, my span is about from 3 to 6 meters, or up to 6 meters, I could say. Live load usually in the range from 4 kilograms per centimeter squares to about 7. One-way ribbed slab actually can be a little bit longer. You can have them anyway up to 9 meters, but in Jordan, our standard practice, they usually don't go more than 7. Live load can be up from 5 kilograms to about 8.5. Meaning it can go up to 8.5 kilogram per centimeter square. If you take the waffle slabs, for instance, that length could go up to 14.5 meters. And your live load can go up to 10 kilogram per centimeter square. So you can see the range between the one-way slab and two-way slab. Okay, so this is just a brief info. Again, we are more concerned with one-way solid slab, and that's what I have to say about that. Moving on now, I'm going to mention some of the provisions that we are going to need for the design of solid slab, at least in this course. There are more provisions, of course. If you want the full-blown provisions, you can go to chapter 7 in the ACI code, and it will give you in full details what is needed. For me, I just picked a couple of things that we are going to need to do in our course here. For that, I'm going to start off with the minimum flexural reinforcement, what we usually call AS minimum, and that should not be less than 0.00118 area gross. Now this AS minimum, by the way, is different from the AS minimum that we covered in the beams. All right, so these two, the raw minimum or AS minimum in the beams does not carry over to the slabs. Okay, so for the slabs, my minimum area reinforcement that is required is 0.018 area gross, which is mean the gross area. Okay, usually in solid slabs, when we do a design, we usually take a 1 meter width representation. It's usually per meter run. So this is usually 1 meter. Okay. And then if this is, let's say, my height, okay, then my AS minimum probably is going to be 0.00118. Area gross now is times 1 times H. So that's my AS minimum. Okay. Now, shear. Now, it says that we need a minimum area of shear reinforcement, so we don't have what we usually call a required like we did in beams. So this one is a little bit different. So if I calculate V ultimate and it is larger than 5 VC, then I have to provide AV minimum. Okay, and that's it. Right? If it's less than 5 VC, then technically I don't need to provide anything. Right? And during the example, I will clarify that. Now here, again, going back to 5VC, this could be either equation A or equation B, all right? Equation A being the old simple shear formula, which was 0.17 square root F prime C B WAP D. Equation B was the one where we included the reinforcement ratio. So if my V ultimate is larger than 5VC, I have to provide AV minimum. Okay, now AV minimum is the same AV minimum that we talked about in the shear design, which was according to section 9.6.3.4. I think I just put that here so that you don't have to go back and forth to the shear section. But again, these are the two equations that hold. So in our case, we only need these two because we are not talking about pre-stressed concrete in this course. All right, so these are the two equations that we are going to need for AV minimum. Here I would like to point out that D over 2 and 600 millimeters does not apply to the solid slabs because that is pertain only to beams and one-way rib slab, by the way. Okay, so keep that in mind when we get to it. The other thing that we need is what we call the shrinkage and temperature reinforcement. and it is the same ratio, which is also 0.0018 area gross. And this is usually the reinforcement, that the perpendicular reinforcement that we provide in the to the main reinforcement. So if this is my main reinforcement, okay, then I have to provide additional reinforcement, and that's what we call the shrinkage and temperature reinforcement, which should be 0.0018 area gross. Now we also have to keep the spacing between that, and this is the spacing that we are talking about. Okay, so the spacing shall not exceed the lesser of 5H and 450 millimeters. Okay, so we need to keep that in our minds when we do design for slabs. With that, I'm going to start off with an example right away. I have a one-way single span, reinforced concrete. The span is 5 meters. Surface live load is 15 kilonewton per meter square. The dead load is 10 kilonewton per meter square, including self-weight. The F prime C is 22 megapascals. Yield stress for steel is 420. He's asking me to design the slab following the provision of the ACI code. So first off, I really need to find what my thickness is, and for that I'm going to use the table that we talked about in the serviceability. Since I have a simple solid span, then it's going to be L over 20, with L being 5 meters over 20, so my minimum thickness for deflection control must be 250 millimeters. All right, so now I'm going to design for the flexure. Again, I'm taking a 1 meter thickness strip, which means that my B is 1 meter, which means now that my ultimate load is going to be 1.2 dead, which is 10 plus 1.6 times the live load 15, and that will give me an ultimate load of 36 kilonewton per meter run, which means now my M ultimate, since again this is a simple span, it's going to be W ultimate L square over 8, and that's going to be 112.5 kilonewton meters. Here I'm going to assume 0.6 rho max, and that's going to give me this value right here. Using this equation, then M ultimate is equal to 0.9, which is my phi, times rho, times 420, times this is my B. So the only unknown here is D. By the way, this is 22, not 28. The numbers are actually reflected by, I forgot to change that. So D now will become 185.29, which is less than 250. So here actually what controlled was the deflection and not the flexure, by the way. So I'm going to use H to be 250 millimeters, which will give me a D of 221 millimeters. Here, so now after establishing the width, now I'm going to calculate the area of the reinforcement. So I'm going to use my 0.6 rho times 1000 times 217.5. Here again, this was based on 525. So this is now my area of steel. I go back to the tables and I find that the closest is to it is 818. So which means now I have to recalculate the value of D. So that's now going to be H minus, again, we use 20 millimeters as cover for slabs, minus phi over 2, which is 18 over 2, which is going to be 9. So this is now my new D. Now, based on that, now I have to calculate A. A is, just as a reminder, this is the area of steel for the 818 times my Fy divided by 0.85 times F prime C times the width B. And this is going to be 45.72 millimeters, thus C is 53.7. Calculating net tensile the net tensile strain for the steel, I'm getting 0.009, which means that my phi is 0.9. Now I have to check if my rho is adequate or not. I'm using this area of steel of phi 18 divided by D times B, it's larger than rho minimum, then okay. And the maximum moment this provides is 152.48. It's a little bit more than needed, but let's move on and continue. So now I have to check the spacing, and if you remember, these two equations were based on crack control. So here I'm not going to calculate Fs, and I'm going to use 2/3 of the Fy. So, and again, this is my clear cover, the 20. So I have 330 and I have 300. So S required for crack control is 300 millimeters. So I'm taking the lesser out of this one and that one. Okay, now the provided S, which I have, so based on the design, my width is 1,000 millimeters minus cover 20 from both sides minus the number of phi, which is 8 times 15 divided by n minus 1. So the provided is 116, which again is less than 300, then that's fine. It's okay. Again, I did not like the ultimate moment. I thought it was more than 10%. So I used the raw formula, the one that I gave you in the flexure part. And from that, I calculated area of steel directly. And instead of having 8 phi 18, I'm getting 6 phi 18, which will give me an ultimate moment of 117, which is a lot closer to 112. So I'm liking that much better. Again, if I calculate the provided spacing, it's 170.4, so it's more than the 116, but still less than 300, so I'm fine. Now, shear. Now, if I calculate V ultimate is about 82 kilonewton, which is simply your WL over 2. Okay. Now here I calculated 5 VC using equation A, and that was around 131 or 33 kilonewton. I'm not sure, so you guys check that out. It's simply 0.75 times 0.17 times square root of F prime C B times D. So here technically I don't need to use any shear reinforcement. But again, according to the shear equation, FAV minimum, and that's also new in the code, is equal to 0. I need to check equation C. Okay, so I did, and I calculated 5VC according to equation C, and it was 93.93 kilonewton, which is still larger than my V ultimate of 82 kilonewton, so I really don't need to use any shear reinforcement. Okay, so in the past, before 2019, you would just compare with 5VC, it was less, no shear reinforcement required, and move on. Now you have to also check for 5VC equation C if you are going to use AV minimum. Again, like I said, although we know in slabs the shear forces get redistributed, but still higher reinforcement ratio usually tends to lower the thickness of the slab. But again, and we talked about that before. So just to re-emphasize, for shear calculation, number one, check V ultimate against 5VC, which is either equation A or B, and in this case I used equation A. If that's less, then you go back and check with equation C to make absolutely sure that you do not need any shear reinforcement. Another example, let's say I have a reinforced concrete slab. It's built integrally, okay, with its supports, and consists of 2 equal spans, each with a clear span of 4.5 meters. The surface live load is 5 kilonewton per meter square. Here I'm using F prime C 21. Here the concrete density is 23.5 kilonewton per meter cubed, which means he wants me to calculate the dead load. I'm using 420 my yield stress. Design following the provisions of the Aci code. Okay. So again, first I'm going to start off with finding out what the thickness, minimum thickness is for my slab. Here I'm using the one end continuous, which is L over 24, 4.5 divided by 24. So I will be needing at least 180 millimeters. So I'm going to use H to 200 millimeters. Based on that, I can calculate now the dead load. That's going to be 23.5 times 0.2, which is going to be 4.7 kilonewton per meter square. So the ultimate load is 1.2 times 4.7 is plus 1.6 times 5, and it's going to be 13.14 kilonewton per meter square. Now here, I'm not going to use a direct method to calculate the moment. As you said, this is an indeterminate structure. So for indeterminate structure, at least in this course, I want you to use what we call the Aci coefficients. Okay, so what are the Aci coefficients? Now, the Aci coefficients are, again, they are a simplified method for analysis for both beams and one-way slabs. The popularity is in the sense that I really don't need to do any, let's say, quote unquote involved structural analysis. But the problem is we have some conditions for us to be able to use this. So, and these conditions are as follows. Number one, members are prismatic, which means that they have constant cross section all over. Okay, so there is no tapered sections. I cannot allow that. Okay, but again, 99% of our structure are prismatic. All right. Number two, or B, loads are uniformly distributed, which means if I have a concentrated load, you cannot use it. So if I have, let's say, something like this, there's one concentrated load, so these simplified are no more. All right. C, the live load is less than or equal 3 times the dead load. So that's the maximum I can go for live load. So let's say if my dead load is, when I'm just pulling numbers here, let's say 3 kilonewton per meter squared, then the maximum live load allowed would be 9. Okay? And that's per meter square. Again, it's 3. That's the ratio need to be upheld. There are at least 2 spans, and I really don't need to talk about that because that's obvious, because it's one span, it's just simply supported. The last condition, the longer of 2 adjacent spans does not exceed the shorter by more than 20%. So if I have, let's say, these 2 spans, so these are what I call 2 adjacent spans. Okay, so if this is L, this should be less than 1.2 L. Okay. Now, if I have another span right here, then I will compare this span with this span. So again, we're talking about 2 adjacent spans. So the maximum ratio is 20%. Now, what are these? As you know, for continuous beams and slabs, solid slabs, I have positive moment and negative moment. So for positive moment, I have 2 conditions. I have end and I have interior. Okay. Now for the end span, also I have 2 conditions. If it is discontinuous and integral with support, then I'm going to use WL square over 14. If it is discontinuous and unrestrained, okay, so there's no restriction there, or the fixation is removed, let's say, then WL square will be over 11. For all interior spans, it's going to be WL square over 16. Okay, so that's if I'm talking about positive moment. Negative moment, for negative moment I have, again, if I have an interior face of an exterior support, then this also have 2 conditions. Remember, built integrally with supporting spandrel beam, and that's going to be WL square over 24. If it's member integrally with supporting column, then that's going to be WL square over 16. And I have an example to show you how these numbers are drawn. Okay. If I have an exterior face of first interior support, then if it's 2 spans, it's going to be WL square over 9. If it's more than 2 spans, it's going to be WL over 10. If it's for face of other supports, then it's going to be WL squared over 11. Okay. Again, it will be better if I show you an example how to use this table. Now, as far as shear is concerned, for shear I only have two conditions. If it's at the exterior face, which means the first column, then it's going to be 1.15 W ultimate ln over 2. And the face of all other supports is just going to be WL over 2, which is just simply the shear equation for the simple beam, okay, except for this one, or for the first support, of course. Now, in my case, again, here I have the negative moment. So since this is a spandrel, so this is going to be WL squared over 24. We said for the first interior support for positive moment, it's going to be WL over 14. And then for if I have a 2 span, then the face is going to be WL squared over 9. So calculating the moment according to that. So at the interior support, again, it's going to be 1 over 9 times W 13.14 times the length, which is 4.5. Again, ln is the clear spacing, and that's my ln. So from the face of the support to the face of the support. So now I have these moments. I'm just using their coefficients instead of using a lengthy indeterminate structural analysis. Okay. So now, according to that, my maximum moment is 29.57. And I'm going to start with that. So here again, I'm using 0.6 rho max. D now is 200 minus 20. And here I'm assuming 12. So this is my D. And according to that, my area of steel will become 463, which is again bigger than the AS minimum, which is calculated to be 313.2 millimeters squared. So here I'm going to use 5, 12. All right. Again, here I use the same technique that I used in the previous example to find AS, area of steel. Now I have to check with phi. Then I go with finding A, C, net tensile strain, and M ultimate now is 35.77. Okay, which is again very large opinion. So again, but still moving on, and I will show you why I did not change it. Now, using for mid-span, you can notice that the area of steel is 294.7, which is less than the minimum steel. So for that, then I have to use the minimum steel, which is 3.512. The exterior is 170.5. And I have to use also 3.512 per meter. Now for my shrinkage bar, it's going to be simply 0.0018 area gross, which is B times H. Again, this being 1,000 millimeters, and H being the 200 millimeters that we found. This is 360, so I'm going to use 4.512 in the perpendicular direction. If you calculate for shear consideration, again, AV minimum is 0, so I'm going to use 5VC equation C. Okay. Now V ultimate is going to be again using the exterior. It's going to be 115 times W ultimate ln over 2 minus W ultimate times D, and it's going to be 31.71 kilonewtons, which is less than 58.7, so I don't need no shear reinforcement. Okay, remember, of course, first I calculated 5VC using equation A, and I found that to be less than the ultimate, so I would excuse me, I found 5VC to be larger than the ultimate, so I would not need AV minimum, but then again I have to check with 5VC. So again, you need to check both of them. Okay. Now going to the spacing, again, required I need 330 or 300, so the minimum is 300. So now I go to provided, which is the 1000 B minus the cover minus 5/4. I'm getting 225, which is less than 300 millimeters, so I am in the clear. Now if I go to the minimum reinforcement, which was my 3512, what do I notice? I notice that the spacing is 462, which is larger than 300. So now I'm bound, because of my provisions, for the crack control to be not more than 300. Then I'm forced to use, again, 5/12. So just one of the notes here, although we do not need 5/12 for the other moments, but because of the crack control, which dominated here, I'm using 5/12, which means this slab in particular, there's no problem in the flexural design. So we needed AS minimum to begin with, because the moment was small. And then we found out that because of the crack control, I'm even going to need more steel. Okay? So if you want to go back and calculate M ultimate, which is going to be a much, much larger than what is required as far as flexure is concerned. But because of the crack control, I have to use 5/12. Okay? So this will be the end of this session. I wish you all a very good